detail here as the quarter goes along. It'll take me about a week or so to get to them. But it's the way that people now do these surfaces. They do them with subdivision surfaces. And the idea is always to take something and try to get a 1/3, 2/3 type algorithm to see if you can make these things work. Okay? But you don't usually find subdivision algorithms in OpenGL. And the problem is you have to then be able to do it yourself. And that is where the problem comes, is doing these things yourself. Okay, so here's one. It's just a ruled surface. Okay, the one that most people use is called a Bezier curve, or a Bezier patch. Okay, and let me review the Bezier curve for you first. Okay, the Bezier curve looks like this. Okay, the Bezier curve looks like this. You take control points, like this, and what you do is you don't do the 1/4, 3/4 algorithm. You do the, I call it the half, half, half algorithm. Okay, that you start taking points halfway along here and connecting the dots. Take points halfway along here, connect the dots. And when you do the last one, that becomes a new point on the curve. Okay? That becomes a new point on the curve. And then what you can do is you can split now the curve into two pieces. Right? Because you started with 2 points here, and we always assume with a Bezier curve that P0 and P1 are actually on the curve. On Chaikin's curve over here, the initial points weren't necessarily on the curve. In fact, they weren't on the curve unless you did some really interesting things with them. Okay? Here, these points are always thought to be on the curve, which is actually kind of nice, okay, that these points are actually on the curve. These points are not necessarily on the curve, okay? They aren't necessarily on the curve. And so you have 2 points on the curve, two other control points, and when you do this half, half, half split, you end up with being able to split here, having 2 points on the curve and two new control points, or 2 points on the curve and 2 new control points. Okay? And what this does is, you can do it again. Okay? Bing, bing, bing. Half, half. There's another point on the curve. There's another point on the curve there. And you can keep doing this, right? This nice step until you get sufficiently large numbers of points. Here, sufficiently large number of points, then we just connect them up with straight lines, okay? And you can kind of see that as you keep going here, that these initial points, if the curve looks like this, right, these initial points are kind of far from the curve, but notice as you start doing this process, these points start getting closer and closer and closer and closer to the curve. Okay? And so actually at some point stopping this whole process and using the little control points, all the remainder of the control points that you have, and drawing straight lines between them is actually a reasonable approximation now of the curve. Okay? This is why we like Bezier. We like it for a lot more than this, but this is one of the reasons we like Bezier. You can actually fix the endpoints. Okay? You can fix the endpoints, but then as you subdivide, these control points kind of converge to the curve. Okay? In the limit they do, of course, converge to the curve, but in general they get closer and closer and closer, and pretty soon they're so close that you don't care. Okay? And you draw them. Now this curve has a lot of very nice properties. For example, if P0, P1, P2, and P3 are all collinear, okay, then you would hope that you get a straight line. Right? And it's not too hard to see that you actually do get a straight line, because if these things are all collinear, then if I take midpoints, they're still on the same line. Everything's always on the same, on that line. Okay? And that's actually kind of nice that it reproduces linear for you. At least it reproduces something. There's also a thing with this that there's something called the convex hull property. And that says that if I take the convex hull of some points, if I take a bunch of points here, the convex hull of these points is the smallest convex set that contains them all. Okay? It's the smallest convex set that contains them all. Now, a convex means that if it can't be like this, right? That's non-convex. If you take any point in one side, any 2 points in them, they have to be connected by a straight line that goes all the way through. All right, that always stays inside. So the smallest convex set is what they call the convex hull. And if you go talk to Dr. Armenta in the CS department, she studies things like this. How do you calculate the convex hull quickly? But this has the property that if you take the convex hull of all the control points, no matter how many you have, right? If you take the convex hull of all the control points, then the curve is going to lie within that convex hull, which is kind of cool because that means that the curve doesn't get away from you very much. Okay, it's guaranteed not to get away, right? That if you can take the smallest convex set, well, we don't usually take the smallest one. What we usually do is take a simple one, like a box around the control points. Right? The convex hull is the smallest one. A box is convex. It's perhaps not the smallest, but it's convex. So we take a box around it. The curve is always guaranteed to lie within the box. Okay, so the great thing about Bezier is the curve is not getting away from us. There's other curves out there. They can get away from you, okay, very badly. And the ones that the math department likes to teach in the numerical analysis course are some of the worst, okay, that they can get away very, very badly. And they're called interpolating splines. And if you look at something like this, where maybe there was a slight error here, right, in these control points, they would their curve would look like this. Okay, and you can see that if you took the smallest convex set containing these points or something, the curve gets way outside. We want the curve to stay, our curve stay inside. The Bezier curve also has another property called variation diminishing. Variation diminishing means this, that if I run a line through here, okay, any line, run a line through there, and I count the number of times that this line intersects this initial polygon that I put in, okay, it's guaranteed that it will not intersect the curve more than that. That makes sense? It intersects the curve less than or equal to the number of times it intersects that original polygon. And what that means with Bezier curves is they don't wiggle, right? If you had a curve that really wiggled, right, you could run a line through there and it would intersect a whole bunch of times. Right, so Bezier curves are really nice. They stay where we like, right, and they don't wiggle. Okay, this one wiggles. Right? I mean, it really wiggles. So the Bezier, that's what we really like about Bezier curves is these properties. Now, it goes through the endpoints, right? You can vary things around a bit. Okay, it's not too hard to see, I don't think, that. Let me draw another one over here. Okay. If I draw another one, it's not too hard to see if I draw this. I'm going to pretend it goes like that. Okay. If I draw this, it's not too hard to see that the tangent line here at P3, right, has got to be the slope of the tangent line actually has to be the same as the slope of the line P2, P3. It's not too hard to see this because I'm always taking half, 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 and one of my half points is always on this line, right? So it's going to approach the line here. Same thing over here, that the derivative over here, the slope of the tangent line, is the same here. So we kind of know how tangent lines work with Bezier curves. They work pretty well in general. And if you remember, we could actually write down the equation of this puppy, right? And it was actually pretty easy to do. If you wrote something like this, it was 1 minus t cubed in this case, p0 plus 3t squared, 3t times 1 minus t squared, p1 plus 3t squared times 1 minus t p2 plus t cubed p3, okay? Was that one. And this is one of those cool, if you remember this was cool, this was an affine combination because all the coefficients here added up to 1. No matter what t is, the coefficients always add up to 1. And you could actually write this down. If you wanted to take the derivative here, you would find that the derivative of this thing at 0 happens to be 3 times p1 minus p0. And the derivative here at over here has happened to be 3 times p3 minus p2. It does have the slope, the correct slope, okay? So the problem becomes when you start piecing these guys together, okay? And oh, by the way, you know, you might think that we're going to be able to write down what this is in surfaces, and we'll be able to put texture coordinates on these things too, and have them act correctly, okay? Which is the other reason we like Bezier, okay? The problem is when you want to stitch these two guys together. So suppose we have one here, okay? And we have another one here, okay? We have another one here. Well, in order to stitch these guys together, here's one, here's two. In order to stitch two of these curves together, you've got a problem in that you want it to be smooth here. Okay, you want a kind of a smooth join here. Okay, if you have this case, like this, here you have this one, and then you have this one. At this point, you're going to have one curve going this way, and you're going to have one going this way, and you're going to have a cusp here, right? You're going to have a cusp. Cusps don't look good on smooth things, right? And so you can see that in order to do this, you're going to have to exploit this thing that you know, that the tangent line here is parallel to this, and the tangent line here is parallel to this, right? And these 3 points better be collinear, okay? These 3 points better be collinear when you start stitching these things together, okay? And you can happily do that as long as those points are collinear. One of the things that you can do is when we start texturing things, they're going to vary over something. And one of the things you can also do is you would like the derivative here not only to be collinear, you'd like the derivative to be the same coming in and out of this point. And so we typically do that by making sure that these two lines here are exactly the same length. Okay? If these two lines are exactly the same length, then the derivative on one and the derivative of the other are identical. So this means that not only do they come together, but their first derivatives are the same. Okay? And those are the things that we usually like to do. Actually, in many cases, we want the second derivatives to always be the same. I'm going to avoid that one for this class, okay? Because then, if you want the second derivatives to be the same, then these points have to be constrained a little bit too. And then it gets dicey. And if you want the third derivatives to be the same, then you get basically one curve. There's only one curve that fits the whole thing. Okay? It constrains everything. So Bezier curves are cool, and we use them a lot. And we use subdivision curves a lot too. The biggest thing on Bezier curves that people don't like is the fact that they're hard to piece together. Okay? And there's something out there called NURBS. Okay? There's something out there called NURBS, right? Which is something for uniform, thank you, rational B-spline, okay, non-uniform rational B-splines. And these things are basically Bezier curves already pieced together for you. Okay? Now, this is a graduate course. The last part of an undergraduate course and a graduate course to actually get you to these things. But what you have, if you remember with Chaikin's curve, what you resulted in was something that looked like little curves like this, like that, like that, like that, and like that. Okay? And what you had in between at each one is you had these quadratic, these parabolic pieces in Chaikin's curve. Right? You had little parabolas all pieced together. But we could specify just these Chaikin's points, okay? And we kind of automatically, when we did this, got all of these quadratic pieces pieced together. Turns out all these quadratic pieces are Bezier curves. Okay? And so what we've done over the years is we've figured out how to put all of these things together, okay, and get a general curve and put other types of curves in here also, not just parabolas. Okay, and these are called non-uniform rational B-splines. And actually, most of us usually do UBS, okay? UBS, we do uniform B-splines, okay? We don't do rational, and we don't do non-uniform. Most people do UBS, okay? And also, I'll show you with UBS, okay? So in general, with these guys, and by the way, there are OpenGL functions for all of these things. All right, there are OpenGL functions. You just have to put the right parameters in them. But with UBS, you have to, with B-splines, you have perhaps more points, like this, okay? You have perhaps additional points. And what you can get is you can get a set of curves that go through here, like that, okay? You get a set of curves that go through here, so, and it is Bezier curves pieced together. And you have to give it a little bit of information as you do this, okay? You have to give it the set of control points. You have to give it the type of curve that you want to piece together, right? If it's quadratic, right, you want to tell it it's degree 2. If it's cubic, you want to say it's degree 3, etc. You have to tell it that. And people usually tell it by what we call the order. And the order is the order k, and that is usually specified as the degree of the curve of the subcurves plus 1. Okay? So when we want cubics, we say order equal 4 here. It's a long story of why we specify 1 more than the degree, okay? Which you have to go back to 1946 to explain how the math started, okay? But this is what we specify. And then we specify something called a knot sequence. Oops. Okay? And the knot sequence looks like something like this. In this case, okay? And you say, huh? Right. The knot sequence looks something like this, okay? Oh, this is actually, well, this is non, okay? Okay? Here's a non-uniform knot sequence. Here's a uniform knot sequence. That's a uniform one, okay? Now, I drew this particular picture out so you can kind of get an idea how this goes. If you look at this, this is really I meant this to be 2 cubic pieces pieced together, okay, nicely. That's the way I meant it. And it goes through the endpoints, all right? Now, in this, in this sequence right here, can you see that here's your 2 pieces lying in between 0 and 1, and the other piece lying between 1 and 2? And when you repeat the knots like this, what it does, if you repeat the knots k times, it forces it to go through the endpoints. Okay? If you don't repeat the knots, it does not necessarily go through, and probably never does go through the endpoints. So in the uniform case, right, which is Chaikin's curve is a uniform case, it doesn't go through the endpoints. Okay? In the Bezier case, we always have these knots, right, duplicated 4 times for cubics, 3 times for quadratics, etc. It goes through. So most of us build a knot sequence just looks like this. Okay? And if we want 6 or 7, if we have, it depends. If you number you can number them similarly here. Knots, usually numbered T. Like that, okay? And usually this number, right, minus that number equals that number minus 1, okay? Or this number plus that number is 1 more than this number, okay, to get the pieces right. Now I'm being confusing and I'm trying not to lecture on this, okay? This is 4 weeks of a graduate course that I'm doing here in one panel of the blackboard, okay, of why these things work. But there is a way. The math, and by the way, when we did all these things, we got this nice math over here, right, for Bezier curves. The nice math is gone. Poof. Okay? It is absolutely, completely gone with these guys. But you get a really nice formulation of how to make a curve. And the great thing about it is, if I had 27 points over here, right, I would get a 26th degree polynomial when I did it. Over here, I can say I want k equal to 4 and I don't want any polynomial bigger than 3, right, in here. Okay, and so you get much faster operation with these things and all. Okay, and they're called NURBS. Everybody calls them NURBS. If you look out on the OpenGL manuals, they're called NURBS. Okay, everybody calls them this. And probably most of the appliances you have in your house have been designed with these. Every single CAD package that's out there. I bought a vacuum cleaner and it came with a picture of them using the CAD package, right, to do it. If you fly on a 777, right, it's all these guys. Okay, it's all B-spline curves. Okay, and the B-spline, they're very, very nice. The B-splines have the same property that Bezier does in general. First, if they're all collinear, the B-spline, well, they're pieced together Beziers, they got to be linear too. Okay, it has this property, the convex hull property. If you put a box around it, right, around all the control points, then the curve has to stay inside the box, right? And if you run a line through here, it has to hit the curve less than or equal to the number of times it hits this actual straight line polygon. Okay, so it has the variation diminishing property and everything else. And why? Well, of course, you're piecing together Bezier curves. Okay. Those of us that do lecture on the mathematics of this stuff, the mathematics goes to hell. Okay, just absolute. I mean, you can do it, right? You can do it. I have this one lecture that just blows everybody out, and you just give it because they'll have to see it 3 or 4 times before they can actually understand it. But I mean, you can do the math, and it's horribly messy. But the nice, beautiful math basically is gone. But you can still do these things. And how do they do them? It's not much of a mystery on how they do them. They break them up into the Bezier segments, okay? And then they run the Bezier algorithms on them, okay? And they can break them up very nicely in general. So, you know, these are some things you should look at, right? All you need to do, the only things you need to do is need to tell it what the order of the curves are that you want, right, or the degree, and you need to give it this knot sequence, which kind of forces it to go through. By the way, if I had 4 1s in here, right, and one of the control points would also go through the curve, be on the curve. Okay, and you need to experiment with them a little bit, but they are the same thing as Bezier curves. Okay, so those are curves. And we have subdivision curves, and we have Bezier curves, and we have B-spline curves, or NURBS, right? We can do the same thing with surfaces. Right? We can do the same thing with surfaces. So here's what you do is you specify a three-dimensional array of points for these things. So here's, I'll say there's P00, here's P30, P33, P03 here, P10, P20, P11. Get the idea? Okay? You specify a two-dimensional array of points. And these things can be anywhere in 3D, as can the points on a regular Bezier curve. They can be anywhere in 3D. And you get this basic three-dimensional set of points. Now, the Bezier curve has the Bezier patch, we call it. These are called patches. The Bezier patch has all the same properties that the curves do in 3D, however. Okay, so they have the fact that if all these points are planar in one plane, right, then the entire curve also is planar, or the entire patch, sorry, is planar. That if you put a box around them all, that the patch stays within the box. Okay, and then you run any ray through this patch, no matter how, it's going to hit this. It's going to hit these polygons here more than it hits the curve. It gets a little nebulous as we run around. Okay, most people stop at patches. There's been a few of us, and we're famous for this at UC Davis, went up and tried to do it not a 2D array, do a 3D array. Then you get this Bezier solid, right? And you can kind of envision this thing of Jello, right? This little cube of Jello that we can push and pull the points back on and make our Jello wiggle. Okay, you can kind of do that. We actually made some real things out of it, but anyway. But most people stop at patches, and what they try to do is get the surface patches to go. And the evaluation mechanisms for this is actually really easy. It's what we call a tensor product patch, okay, meaning it's kind of loosely, it's curves in one direction, right, kind of bonded with curves in the other direction. All right, so the boundary of what you get here with this thing, on the boundaries here, you take these four and you get a Bezier curve on the boundary. Okay? You get a Bezier curve going this way, and this way, and this way. Okay? You get, again, use your imagination. Okay? You get a Bezier curve on the boundary. This line here is tangent to the curve, right? This line here is tangent to the curve. And that's why I say use your imagination. Right? These are tangents. Okay? But everything you can think of, the curves match up really nicely. The way you evaluate on this is you do the following. If you want to evaluate the point at a half, or something like this, what you do is you evaluate this curve here at a half. Right? You evaluate this curve at a half in this direction. And then you think of curves sitting here and you evaluate them in a half and a half. Now these guys don't necessarily touch the surface. Only the four corners touch the surface. Okay? And then if you do these, then in the other direction you look at this curve and you evaluate it at a half and you get the point on the real surface. You can do it, the moral of the story is you can do it all with curves. Okay? You don't need anything, you don't need any super patch math or anything. You can do it all with your curve algorithms. So if you have a set of Bezier curve algorithms here, you can do everything that has to do with these guys, right, in your curve algorithms themselves. Now there's a whole set of corresponding algorithms that go along with these guys also. Okay, and let's see. Normally you think of this as going. There's a parameter u. There has to be two parameters now on a surface, right? A parameter u in one direction, and a parameter v. And so you get out something called p of u and v. Okay? And this you can actually write down in most cases. I'll write it down. Don't copy this down. I'll do 3. Of P, I, and J, and B, I, J, O, T. You can actually write down a math equation for this. Now, this looks kind of weird, but the BIJs look like something called n choose I times 1 minus T to the n minus I and T to the I. Where's J? There's oh, okay, I got it. BI of T. There's another one, BJ of T. There you go. Now this should be I and I. It looks like that, okay? And this is, if you look at this one, this is the 3t times 1 minus t squared, right? That's what that is. These are all these functions. The coefficients that went in front that added up to 1. And what I do in a patch case is I just multiply them together. I take all the ones in the u direction and multiply them times the ones in the v direction, and that gives me the things that work in patches, okay? And you can see if we wanted to go up another dimension, you'd have 3 of them, right? But they really have to do only with the curves themselves, okay? Because you multiply them together. And patches work, okay? They work really nicely. But they've got this, they've got a few little things that don't do well. We have what we call a subdividing algorithm. If you remember with a curve here, we could split by taking halves here and halves. We split this curve into 2 pieces, okay? We can do it exactly here also by splitting all the curves first in one direction, okay? And we'll get, we can split it into 2 pieces by splitting all these edges, these rows, and then we can split the columns in the other direction. And we can get, so we can actually split this thing into, say, 4 pieces pretty easily. And a lot of the algorithms in graphics have to do with patches, and they split them into 4 pieces. And then they split them again. And this is where actually the word subdivision comes from, is splitting these patches. These were all basically invented by a guy named Ed Catmull, who is the CEO of Pixar. Actually, no, Steve Jobs is the CEO of Pixar. Ed Catmull's the president, okay, of the company. But this was done, all this subdivision stuff and everything was done with patches in his PhD thesis in, I think, 74 or so. But now, here comes the problems. Suppose you want to have 2 patches, right, come together, okay? Suppose you want to have 2 patches come together and be smooth, okay? Now, I'm drawing patches with 4 points here, which are really what we would call cubic patch. These are off the, do I have enough? No. There. Okay? So if I had a 3 by 3 set of patches here, okay, and you can do 3 by 5 and everything else, it's just these numbers aren't 3s, they're 5s. But if I want to make sure that this thing is smooth going over here, that I don't get a seam, right, or a cusp, what I have to do is I have to make sure that every single one of these things, that these guys are all collinear, that these guys, are all collinear. I also have to make sure that these folks are collinear, and I have to make sure that those folks are collinear, okay, in order to get this thing smooth. And you can see if you're doing this by hand, all of a sudden this starts to get a little rough, okay? And actually, if I want it really smooth, I want the derivatives to be the same as I go over, right? I've got to not only make sure that those are collinear, but I've got to make sure that they are the same length, okay? And now all of a sudden it gets harder and harder to specify, once you got these patches, and if you stop to think about it, you've got maybe another one down here, maybe another one down here, you're trying to piece these things together, okay, and all of a sudden you're in trouble, okay, because you're trying to figure out, this guy has to be collinear over here, and, all of a sudden you're in trouble, and you got a big mess. And so the nice thing about it is that we have NURBS surfaces also, okay? And the moral of the story is you can pick any number of control points, right? Any two-dimensional array of control points, right, etc. Any two-dimensional array of control points you want with any number of control points, okay? Now you have to tell it a few extra things. In the curve case, we had to tell it the order, right, of these patches, and you could actually tell it if you wanted to, an order you wanted it in the U direction and an order you wanted in the V direction. We usually don't do that. We usually tell one order, right? So we say, okay, K equals 4, meaning we want cubic pieces to do this. And then you have to give it these knot sequences, but you have to give it 2 knot sequences now, one in the U direction and one in the V direction, which kind of makes sense. Right? And you can make now these patches with arbitrary control points. And what do they do? Well, the very first thing they do is they split it up into Bezier patches, right? And then they just use the Bezier patch algorithms that they've got. But you don't have to do that. The split up is done all actually in the GPU. Okay, it's split up very easily. And again, that's a graduate course I'm giving next quarter. But there are nice algorithms to show you how to find the patches. The Bezier patches from the B-spline patches. There's actually fairly straightforward algorithms. So here you have one order. You usually do an order, which again is the one more than the actual degree of the polynomials that are used, and then you give 2 knot sequences. And now you can do things that are really pretty huge. Okay, so many of us have routines that we develop a Bezier curve with. Okay, just a simple thing: specify the 4 points of a Bezier curve. Now specify a B-spline curve. Now specify another B-spline curve shifted over here, shifted over here, shifted over here, and shifted over here. Combine those all together into an array, right, to give you a B-spline patch. And now you have a kind of a ruled B-spline patch, or whatever, that you can use. And so we actually use, how do you shift it over here, shift it over here, shift it over here? You use transforms, okay? We can do Bezier curves and all with how do you do this? You can rotate things a little bit, your control points, okay? And you get things to kind of move around. Let's see, a circle kind of looks like this. Bezier curves kind of look like this. Here's the circle. It would kind of look like this. Okay. Now, unfortunately, it takes a little while to prove this, but you can prove with a corner cutting algorithm you can never get a circle out. Okay. It'll be close, but it'll never be a circle. And I think I think it's square root of 5 minus 1 over 2 or something you can show is the best you can do on this length in order to get a circle. And you really can't tell the difference that much. But, you corner cutting algorithms, you can't get circles out. You have to go to the rational form, and we generally don't want to do that. But you can do circles. You just have to figure out how to modify the control points a little bit. So if you had several control points here, right, on this, you could rotate it a little bit, right, expand it out a little bit, and do that a couple times, and you can get yourself almost a quarter of a volume of revolution very easily. Now, so you're going to have to play with these things to get them to work out, okay? But just remember, the take-home message on this lecture is, you know Chaikin's curve now, okay? There is that. And you can take that. We now know Bezier curve a little bit better. You can lift those up and do, I'll do subdivision surfaces, which are lifted up Chaikin's later. But you can lift up a Bezier curve to a Bezier patch, right? And get a Bezier patch. That's easy. You can also kind of combine a whole bunch of Bezier curves together into a NURB, into a NURBS curve, right? Of which they're really just pieced together Bezier curves where you don't have to think about the derivatives, okay? So they piece together smoothly. And you can do that fairly easily. And then you can lift these NURBS up into NURBS patches, okay? And about 90% of the work you see in the graphics world is NURBS patches, okay? That's what they actually use. The greatest thing about it is, too, is you can assign texture coordinates to the corners, okay? Texture coordinates to the corners, and you can get a texture to go over here very nicely. Because all of the algorithms they use to split things up work very, very nicely this way. You can also do a lot of things with these guys. All the lighting and everything else that you do, and you should go discover GL diffuse, GL specular, GL. It's not called glossiness. What is it? Shininess. Yeah, shininess. You should go look at, check those out. But all the lighting is done very nicely on this, because what really happens way down in the graphics engine is they break these things all up into little tiny triangles. Okay? Little tiny triangles have normals. You can get the normal out really quick, and you're off. Okay? And so you can get the normals at the corners here really quick, because you know that this line is tangent to the surface, that line's tangent to the surface. Take the cross product of those two vectors, and you can get a normal to the surface at that point. So at the corners, you can get normals. Inside, you know, it's kind of weird. So this is Bezier curved surfaces, NURBS curved surfaces, and I just did about 6 weeks of lecture in one, okay, in a graduate class. I don't want you to know how NURBS are done mathematically or anything else, but there are pieces of code that you can use, and you can experiment with them and everything else, and they do what you would expect them to do. There's no surprises with these things. They don't have funny cusps anywhere. If you lay them out, they actually look very nice. The only caveat is you got to do these knot vectors, right, which kind of tells them how to parameterize themselves. The knot vectors do. Okay, if it's a uniform knot vector, it's going to look like Chaikin's curve. It's going to pull away from the points, right? If it's this 0, 0, 0, 0, 1, 2, 3, 4, 4, 4, 4, or something like that, then it's going to act like a Bezier curve. Okay. So, all right, I'm done, and I will see you. It's Friday. I will see you next week.